Frank Ling.
And I'm Charles Lee.
And you're listening to the Groks Science Show.
That's right. It's a weekly look at the world of science, technology, and their effects on our daily lives. Coming up on today's program, Chad Orzel will join us to discuss Breakfast with Einstein.
So stay tuned for all of this.
Plus the Grokatron 5000.
And our world famous question a week.
Coming right up.
Here.
On the Groks
Science Show.
Welcome back to the Groks Science Show. Well, the world of quantum physics may be thought of as esoteric, but what can the laws of quantum mechanics tell us about everyday objects? Well, in the new book, Breakfast with Einstein, Professor Chad Orzel explores the topic for a general audience. Professor Orzel is a physicist, professor, and blogger, and author of Breakfast with Einstein, How to Teach Quantum Physics to Your Dog, How to Teach Relativity to Your Dog, and Eureka, Discovering Your Inner Scientist. He's currently an associate professor in the Department of Physics and Astronomy at Union College in Schenectady, New York. And Professor Orzel, very pleased to have you today on the Groks Science Show.
Thanks for having me on.
Well, certainly our pleasure. Certainly a fascinating book you've written here, Breakfast with Einstein, The Exotic Physics of Everyday Objects. I'm curious, why did you decide to write this book?
Well, one of the things that you see a lot of in popular discussions of quantum physics is really emphasizing the totally bizarre nature of the theory, which leaves people with this impression that it's something that nobody has any hope of understanding. But if that was really true, we never would have invented the theory, right? Because if it was something that you needed, $1 billion particle accelerator or a whole bunch of lasers and vacuum systems to be able to see, nobody ever would have invented it. So there have to be clues to quantum physics that show up in the behavior of everyday things because, scientists inhabit the same world as everybody else. So we know that quantum mechanics behaves in these really weird ways on a microscopic scale because we were led there by clues that show up in the behavior of ordinary objects. And I think that it's a thing that doesn't get enough attention, that in fact, when you look at the world around you is thoroughly quantum. It's just largely hidden by the fact that most things are kind of big and hot.
Do the same rules that go on at sub-microscopic level apply with quantum mechanics to what we see in everyday life?
Absolutely. The laws of classical physics that we see in some sense are really just what you get when you take the quantum mechanical rules and apply them to, too many particles, right? You take lots and lots of single particles that behave like waves and start sticking them together. What you end up with is something that hides the waviness of that thing and instead starts to look more and more like a particle, like what we think of as an ordinary everyday particle.
What really is the benefits of quantum mechanics in terms of our understanding of the world, and what does it tell us in terms of how we understand everyday objects?
Well, the most important benefits of it really are that the fact that we understand quantum physics allows us to make a whole lot of technological things that are incredibly important. For example, you and I are talking over fiber optic telecommunication lines, right? Those signals that pass along those lines are transmitted through little pulses of laser light. Well, we wouldn't be able to make a laser to carry that signal without an understanding of quantum physics, right? It's the fact that we know that atoms have these discrete energy states and move back and forth between them by absorbing and emitting light that lets us make lasers, and it's lasers that enable the internet as we know it. Similarly, the fact that electrons behave like waves changes the way that they travel through different sorts of materials, and we can exploit that to manipulate the electrical properties of materials and make computer chips out of hunks of solid silicon. And that allows us to do all of the computer information processing that lets you record this and edit it and put it out as a cast for people to listen to.
So really, it's what powers sort of our modern everyday world here.
Absolutely. It's the fact that we know that light has particle nature and also wave nature, and we know that electrons have wave nature in addition to their particle nature. Those facts allow us to manipulate matter on in extremely precise ways that allow us to do all sorts of amazing things.
So your book takes an interesting format. You could go through it as sort of a breakfast with Einstein, so to speak. For example, you start out, for example, with the heating element in the stove there. What does that tell us about quantum mechanics?
So the heating element in anything that gets hot basically is an appropriate place to start, because that is the problem that quantum physics was invented to solve, right? Explaining why when you get something hot, it glows that particular color red. That's the phenomenon that Max Planck was trying to explain, and found he could only explain if he did something that turns out to lead to assigning particle character to light. That's the starting point for the whole thing. As a desperate trick, Planck introduced this idea of a characteristic energy for light that depended on the frequency. He never really liked that trick, but a few years later, Albert Einstein sort of picked it up and used it to explain the photoelectric effect, and said, really, we should take this business seriously and say that it applies to the light directly, that the light has this particle character, and then that got the whole thing up and running. Once people had this idea that you can have these systems where energy comes in discrete little bundles, and light has this particle nature, that inspired all sorts of other stuff and really got quantum physics started.
The essence of quantum physics is that the discrete energy levels, or at least...
Yeah. That's one of the essential properties of quantum physics, and that's what gives the theory its name, right? The quantum is from the Latin for how much. And so it refers to a discrete quantity of energy that's characteristic of some particular system. And in general, what we see is that in systems like atoms and molecules and light and in various configurations, energy comes in these discrete little chunks.
What about the sense of smell? How does quantum physics...
So your sense of smell is based on measuring properties associated with molecules that get wafted into the air from whatever it is that you're smelling. And though the shape of those molecules is entirely determined by the quantum character of the atoms that make them up. You go into any science classroom in the US, you'll find like a periodic table hanging on the wall. The structure of that periodic table, these sort of repeating properties of atoms and the different numbers of things that they bind to and the shape of the molecules they form, all of that is determined by the quantum mechanical properties of the electrons inside those atoms. So everything about our ability to detect molecules with your nose is ultimately determined by this quantum character of atoms and the ways that they stick together.
The book is filled with all of these various fascinating areas. Is there one which you think particularly is surprising to people when they hear how much quantum physics plays in terms of its operation?
There's lots of things that are really surprising. I think one of the ones that takes people most off guard is discovering that if you have a modern smoke detector, that depends on quantum physics, because they actually have a tiny bit of a radioactive isotope in there that they use as part of a detector for smoke particles of a certain size, and that radioactive decay that happens, the alpha decay of this americium isotope that's in there, happens because of the wave nature of these subatomic particles in a process called tunneling, where this particle ought to be trapped inside the nucleus, but it's got a tiny, tiny probability of making it out, even though it doesn't have enough energy to do that. And that's what leads to the radioactive decay. And we exploit that, as it turns out, to make a smoke detector work.
The last chapter talks about encryption, mechanics being used there.
That's using the phenomenon of entanglement, which is a thing that was first really clearly described by Einstein as he became dissatisfied with the theory and left to do other things. And it's this idea that you can have particles in quantum mechanics whose states are not determined. Their individual states are not determined. So you have a 50% chance of getting either of two results in a measurement. But the states of these two particles will be perfectly correlated with each other, no matter how far apart you get them. So you don't know what number you're going to get when you measure one of them, but once you get the result for that one, you know absolutely with certainty that the other one, no matter where it is, has given the same result. And this is incredibly useful for cryptography because that's exactly the thing that you need if you want to encode messages, right? You want two people in very different locations to have a series of random numbers that they can generate that will be identical to each other, that they can use to encode and decode the message at opposite ends, but that nobody else in the universe knows. And quantum entanglement is a way to get that by using this bizarre property of particles whose individual states are totally undetermined, but whose states are correlated with each other. Their collective state is known, and that gives you this ability to generate lists of random numbers at widely separated points in a process that seems almost magic.
How much do we really know about what quantum mechanics really tells us about the world we live in?
And that's a thing that remains sort of problematic. There are a lot of different interpretations of how you think about what's going on before you make measurements of things in quantum mechanics, or in the process of making measurements. How do you decide what the outcome of a particular measurement is going to be in reality? That's an area of really active research, and there's a whole community of people who work on these sort of philosophical foundations of quantum physics. The thing that I would say, though, is ultimately we understand it very well in the sense that all of these different interpretations at the moment give exactly the same quantitative results for any measurement that you would care to do. So absolutely everybody will predict the same probabilities of various different outcomes. And we can predict that to just mind-blowing precision, right? There are certain properties of electrons that we can use quantum mechanics to predict what the value of this property should be to something like 15 decimal places. And people can go out and do the experiment and measure that property to 15 decimal places, and they agree with each other perfectly. So we really have an astonishingly good understanding in practical terms of what the theory is telling us. There remain these sort of philosophical issues, and that's a very fruitful area of research that's still going on.
Do you have a particular opinion one way or the other?
I'm temperamentally an experimentalist, so I tend to subscribe to the shut up and calculate interpretation, in the phrase of David Mermin. Which is just to say, look, everybody knows how to get the answers to the questions, and so we can take that fact and we can use it, and we save the talking about what does it all mean and what's the measurement process and how are these things done. We sort of save that for drinks in the bar afterwards and that sort of thing. In the last several years, I've gotten a little more comfortable with the idea of the many worlds interpretation. I think that has some nice features to it, but I'm not super attached to any particular interpretation.
As long as you can use it to run the experiments?
Exactly. The thing I would say about it is that I've written the book so as to take a bunch of very mundane activities and sort of explain here's the quantum physics that's at work in these processes. And my goal with that is really I'm not trying to demystify quantum physics and make it like boring, right? Make it as sort of tedious as the process of getting up and making breakfast and getting off to school in the morning. Instead, what I want to do with the book is sort of make clear to people that this theory is really strange, and yet it's all around you. And I want to sort of elevate the ordinary morning, right? And by knowing a little bit about the quantum physics that underlies all of these very ordinary behaviors, hopefully that makes you appreciate a little more how interesting the world around us is.
And again, we were chatting with Dr. Chad Orzel. He's a physics professor, and he's the author of the new book, Breakfast with Einstein, The Exotic Physics of Everyday Objects. And Dr. Orzel, thank you very much for joining us today on the Groks Science Show.
Hey, thanks for having me on. It was fun.
And that's all for this week's edition of the Groks Science Show.
Make sure you tune in next week for more from the world of science and technology.
If you'd like to contact us here, you can email us at science@groks.net. For Groks Science, I'm Frank Ling.
And I'm Charles Lee. Make sure you also see us on the web at www.groks.net. Have a great afternoon and keep on grokking.